Hey everybody, today we're going to go over area 3 and we're going to start with an example that you should probably know how to do. In fact, it's something that we talked about earlier on in this chapter. How could you find the area of an equilateral triangle? Now, I know it says in the directions, find the area of the following regular polygons. Well, a regular polygon is any polygon that has all of the same side and all of the same angle, essentially. So an equilateral triangle would fit as a regular polygon. So if you were looking at it and you're thinking it's an equilateral triangle, not a regular polygon, it is actually both. Anyway, we have talked in the past, and I feel like we've done it a lot. We've brought up the idea that if you want to know the area of a triangle, you're going to have to do area equals base times height, but because it's a triangle, we want 1/2 base times height. Keep that 1/2 in mind, by the way, because we're going to use that on today's work as well. Now, the height of this triangle, since it is an equilateral triangle, we know that the base is 16, but we also know that the height isn't given to us. So we have to turn it into right triangles. We have to make an 8 right here and an 8 right here. And the shortcut that we talked about in the past, and we are going to practice this some more, is that we would say the height is 8 radical 3. Now, ultimately, the reason that's true is because if you were to go through the process and you were to do 8 squared plus b squared equals 16 squared, you would end up solving and you would get the square root of 192 and you'd have to break it down. The shortcut is way better because now you can just go through and you can say, oh, well, the area is going to be 1/2. I told you we're going to use that a lot. And then the base was 16. And then the height was 8, and then we'll just have to write in radical 3. When you're done, you take all those numbers, you multiply them together. 1/2 of 16 is 8. 8 times 8 is 64, and you end up getting an area of 64, and I'll write it in again, radical 3 centimeters squared. Now, if you wanted to just use the decimal form, you would throw it in the calculator, you would get it that way. In general, I'm going to give you a couple of exact examples today because you might as well get good at that as well. Now, the first example that we just did right now and the second example don't look the same at all, but we are actually going to treat them exactly the same way. We're just going to add an extra step to the hexagon. I've told you all the time, I would rather you be creative in your math than not creative in your math. And that's where creativity is going to come in. It turns out, if you were to take a regular hexagon and you were to break it up, what you would actually get would be 6 equilateral triangles. So even though this first example and this second example don't look the same, they are. It's just with the hexagon, you've got to do it 6 times. So you go over here and you say, well, this is 10, this is 10, this is 10. So I'm going to draw in the height, which would be 5 radical 3, because remember, we break up our 10 into a 5 and a 5. Now all we would have to do is 1/2 base times height. The base was 10. The height was 5 radical 3. And the only difference between the first example and the last example is that if it's a regular hexagon, that means you're going to do it 6 times. That's really the only difference going on here. So we're going to do that same process that we just got done doing. So you've got half of 10, which is 5. 5 times 5 is 25, so we get 25 radical 3. And then the reason this problem is different from the other one is that we are going to multiply that by 6, because what we just did only really gave us one of the equilateral triangles. So if we multiply by 6, that'll give us all of them. So we get 150 radical 3. And then we're going to go with, for the millionth time, centimeters squared. Now, I don't know if you noticed, but in the case of the second example, you can't really do anything that we figured out without that little line that we have right here. I'll make it red just so you can see, just to double check. That was the height of one of our equilateral triangles. So just like in that first example, we couldn't really do anything until we figured out the height of the triangle. Same thing here. We couldn't really do anything until we figured out that distance. Now, in this case, that little line, in the case of a regular polygon, like a hexagon, that line went from the center and it went straight down to the base. Now, this line is so important. This comes up so much in math that they actually gave it a name, and the name is the apothem. A-P-O-T-H-E-M. I've also heard it called apothem, but apothem is what we're going to go with. If you go on a dictionary website or something like that, that's what they'll call it. All right, now, the reason this is significant to you is because the area of any regular polygon, so it doesn't matter how many sides, it could be anything. We use hexagons a lot, but it could be anything. The area equals 1/2. See, there's that 1/2 again. And then lowercase a, lowercase p. So capital A means area, lowercase a means apothem. And in this particular case, P is for perimeter. Okay. Now, the shortcut that we practiced with the height of an equilateral triangle, it really comes in handy a lot. So we need to make sure we're really good at it before we move on. This shortcut is based on 30, 60, 90 triangles. Now, why would they call it a 30, 60, 90 triangle? Well, you've got a 90-degree angle, you've got a 60-degree angle, and if you've got a 90 and a 60, that means the other one is 30. The reason that shortcut is so valuable is because this is what it looks like when you have half of an equilateral triangle. So if somebody told you no other information except, hey, guess what? That's 5. Well, we know that this is half of an equilateral triangle, which means that's 10. And using the shortcut we just got done practicing, that is 5 radical 3. This is incredibly valuable. It's going to come up every time you're dealing with equilateral triangles. It's going to come up every time you're dealing with hexagons. It's going to come up a lot, so you might as well be ready for it. So let's look at the second example. Let's say I told you this thing right here is 12, and then let's just say that I told you this was a 30, 60, 90 triangle. If that's the case, then you can use the shortcut because you know that this is really just half of an equilateral triangle. So if this is 12, this is 6, and this is 6 radical 3. All right, we could do a third example here. Once again, this rule works only in the case of a 30, 60, 90 triangle. So we've got a 30-degree angle here, 60-degree angle here, 90-degree angle here. That means it is half of an equilateral triangle. So let's throw a little curveball in here. Let's say I told you that this right here had a measurement of, this height had a measurement of, let's just say 11 radical 3. That would mean this little guy was just a regular 11, because remember, whatever number is here, it came from the little guy. If you have 6 radical 3, it's because the little guy was 6. If you have 5 radical 3, it's because the little guy was 5. So if you have 11 radical 3, it's because the little guy was 11. And then if it's half of an equilateral triangle, that means that is 22. Now, just food for thought. I'm not going to go over it right now in the video, but I just want you to jot it down. What if something weird happened? What if this was 12? You don't have to worry about it right now. It's not going to help you on the rest of your work right now, but it's something that is definitely going to be extra credit at some point in your life if you have me as a teacher and you are not in the accelerated class. And I can hear them groaning from here because they finally thought they were going to get some extra credit. Anyway, if that was the case, if you had just a plain old 12, the reason this question is a little bit different is because normally we're expecting to have a radical there. What would happen if it wasn't? So that's something, like I said, that'll come up down the line. Now, sometimes that shortcut won't help you, but there is another shortcut that works really well as well, and that's the 45, 45, 90 triangle shortcut. Now, this shortcut only works in the case of, you guessed it, 45, 45, 90 triangles. Now, the key to this shortcut working is that you've got, let's say you've got a 7 right here. Well, if you have 2 of the same angle, we learned way back in the day that you will also have 2 of the same side. Therefore, you'll have another 7. Now, you don't know this yet. Maybe you do. Maybe you've seen it before. The magical shortcut for this, and I'm going to make you do it one time, and then hopefully you'll never have to do this process again because you'll remember it, and it was so easy. 49 plus 49 equals c squared, so that would be 98 equals c squared. 98 is not a perfect square, so if you were to break it down and try to find a perfect square that goes into it, you would discover that 49 goes into 98 twice. So this would, when you solve for it, it would give you 7 radical 2. Wait a second. 7, 7, 7 radical 2. I wonder if that works all the time. I wonder if we could just do 10, 10, 10 radical 2. I mean, I could just make this up for anything. I could just do this little guy over here, and I could just do 2, 2, 2 radical 2. It works every single time. I could put something upside down. And I could do 3.1. I'm running out of room, but you get the idea. 3.1, 3.1 radical 2. It works every time. Now, just the food for thought. If I'm going to give you a question up here that I want you to think about later, let's do the same thing over here. What would happen if you had a 45, 45, 90 triangle? And remember, we're expecting a radical 2 on the hypotenuse. What would happen if this was just 12? See, same number as the other one, but now it's a different type of example. What would happen then? So just food for thought so that we can do our 3 examples and then be done with the lesson. Find the area of each regular polygon. Round your answer to the nearest tenth. So again, your ability to be successful in this lesson depends on how well you remember your special triangles, whether you admit it or not. Because if this is 12 and you want to figure out this line, remember, we break it up. We break up that 12 into 6 and 6, which means that right there is 6 radical 3. So that means the area of this regular polygon, according to our formula, would be 1/2. It comes up so much I copied and pasted it. 1/2 apothem, which we already know that what that's going to be. We know it's going to be 6 radical 3. And then the perimeter is just the distance around. If I have side lengths of 12 and I have to go around 6 times, that means the perimeter is going to be 72. So what you end up getting is an area of 216 times the square root of 3. Half of 6 is 3. 3 times 72 is 216 inches squared. All right, now, here's the thing. It did say this time round your answer to the nearest tenth, which means we are actually allowed to type in 216 times the square root of 3 on our calculators. And if you do that, you would end up getting 374.12 inches squared. So in this case, decimals are allowed. Sometimes I'm going to ask you for one. Sometimes I'm going to ask you for the other. Just be ready. All right. Now for equilateral triangles, I'm not going to have you do the 1/2 AP thing because we are just so good at doing our trick. 10, 10, 10 radical 3. So I'm just going to go back to the 1/2 base times height instead. So if people are wondering, well, isn't it technically a regular polygon? Couldn't you do the other thing? Well, you could, but the line that they gave us wouldn't really work as an apothem. The apothem has to start at the center and go down, and that's not the case here. So I'm just going to go with 1/2 base times height. The entire base is 20. The height is 10 radical 3. Which means the area is, well, half of 20 is 10. 10 times 10 is 100, so you get 100 radical 3 centimeters squared. Now again, in this particular set of directions, it said you should round to the nearest tenth. Apparently, I didn't actually read what I was doing. Tenth would be 1 decimal, so it should have just been 374.1. In the case of this next one, if you did 100 times the square root of 3, that would give you 173.2. And then we probably want to label because otherwise I'm going to get mad and you would get centimeters squared. All right, last example of the day. We've got an octagon. The apothem is 15 feet and S. So we have perimeter, we have apothem. What the heck is S? S is 1 side length. So in a way, this problem is way better than the others because they gave us the apothem. I don't have to do anything cute to try and find it. The catch is they gave us S instead of P. The side length is 11 feet. Well, it's an octagon. It's got 8 sides, and it's regular. That means all 8 sides are 11, which means the perimeter is 88. So you multiply all that together. You can get a calculator out. You don't have to, but you should end up getting an area of 660 square feet. So again, if you're doing it on the calculator, 0.5 times 15 times 88, or whatever order you want to go in, because when you multiply, order doesn't matter. All right, so we kind of covered a lot. We practiced our special triangles, and then we applied that to our apothem for a hexagon. It's going to come up a lot. Be ready for it. Thanks for watching. I'll see you next time.